This video will be a quick intro to the concept of a derivative, and then in future videos we're going to get into the calculations, how do you actually figure them out, and we'll learn some derivative rules. But this will just be about the concept of a derivative. So what is it, and why do we need it? That's the basic question we want to answer here. Now, these gentlemen here that you see on your screen are not members of an 80s hair metal band, but clearly they could have been. They are scientists who lived in the late 1600s and independently developed the methods of calculus that we're going to study. On the left-hand side of the screen, there's Isaac Newton, who's maybe a little more better known for his work in physics. What he did in calculus was in part to help do physics a little bit more efficiently. And then on the right is Gottfried Leibniz, who is more purely focused on the mathematics. They were contemporaries. It's a bit of a controversial topic who developed it first. Did one of them see the work of the other? Were they influenced in one way? I don't know the truth of that, but I do know that they had slightly different paths to the answer, and probably they developed this mostly independently. But they were trying to answer the same basic mathematical question, which is how do you develop a way to calculate the tangent line to a curve and then find the areas under the curves, which I've mentioned before are the two basic things that you do with calculus. And although they seem very specific, are quite broadly applicable to a lot of different physical applications. So who invented calculus? Who developed calculus first? It was these two guys. And whether you give more credit to one than the other, that's up to you. We tend to use the notation that Leibniz developed, and then some of the easiest applications, first applications, were the ones that Newton found. So they both deserve a fair amount of credit for this. Now, what about this business of finding the tangent line? We'll come back to areas under the curve when we get to derivatives, but the first thing that we'll tackle is this tangent line problem. So on the screen here, we have a curve in blue, and it could represent anything, right? It could represent any quantity that's varying. And to be a little suggestive here, we have S and T. So T might be time. So something that's changing over time could be what we're looking at here. And then the tangent line to the curve would represent the rate of change at that particular point. So where a curve is very steep, it's changing rapidly. Where the curve is more flat, it's changing slowly or maybe not changing at all, or if it was going downward, it would be decreasing. So that tangent line is representing something physical about the function. And if it's time dependent, it's the rate of change over time, but it could be the rate of change over whatever this horizontal variable would happen to be. Now I've drawn another line on here. It's called the secant line. Or I say your textbook has drawn another line on here called the secant line. And the secant line is the line that connects any 2 points on the curve. And so there's infinitely many secant lines that you could draw. Now what's the difference between the secant line and the tangent? Well, the tangent is representing at that point what is the rate of change at that point. So where I've drawn it here, I say I again, where your book has drawn it here is at the point A. So this is representing the rate of change at the value A. The secant line then is from A to another point. And so what it's going to represent is the average rate of change from this point to this point. So it's representing average rate of change, while tangent line is representing instantaneous rate of change. Now, if you know the function, calculating the secant line is pretty straightforward. The tangent line is a much harder problem. We'll show that a little bit more on the next slide. But first, just tangent line is running right along the edge of the curve. It's indicating the slope at that particular point. secant line is the line that connects any 2 points on the curve and represent average rate of change between those 2 points. So obviously they mean different things. The instantaneous at that point versus the average from this point to that point. Now, I mentioned the secant line, you don't really need calculus to figure this out because all you need to do to determine the average rate of change is know, okay, where does it end up and where does it start? Right, and so we can find the slope of the secant line just from the function itself. So here I'm going from point A to point X. Now, I don't know why we're changing from X to T, but whatever this variable is, we're going from some value over here to some value over here. And so its change in the vertical direction is the value of the function here minus the value of the function here. So that's your change in the y variable. And then your change in the x variable is from this point to this point, so in this case it's x minus a. So you don't need calculus to find the slope of the secant line. You can calculate the average rate of change just with the function itself. Now the tangent line is something different. It's what happens when you're calculating the secant line but taking those points and making them infinitesimally close to one another. So if you take the secant line and you move this point closer and closer and closer and closer to this point A, you are making the secant line closer and closer to the tangent line. And that is why we needed to learn about limits before we could get to derivatives. The derivative is going to be this tangent line slope, and it's going to represent the limit of the secant line as the 2 points become closer and closer together. And so that's what we're going to do next.